Welcome everyone. In this session, we are going to build a practical mental model of Kubernetes, what it is, how it is organized, and why it matters when we run Kubernetes applications in real environments. At a high level, Kubernetes turns containers into a resilient operating model. A single container is useful, but in real applications need more than just a running process. They need networking, configuration, storage, scaling, release management, security boundaries, monitoring, and a way to recover when something fails. So Kubernetes gives us a common system for handling all of those concerns. The important idea for this deck is that Kubernetes is not just a container runner, it is a control system. We describe the state we want, and Kubernetes keeps working on the background to make sure that the real cluster that matches the desired state. As we go through the deck, there are four ideas we will be coming back always. One is desired state, second is control plane, third are worker nodes, and fourth is the self-healing applications. Mental model. The most important concept in Kubernetes is reconciliation. The Kubernetes is built around the idea that we declare what we want. The controllers continuously compare the desired state with what is actually happening in the system right now. For example, if you say we want, there are three replicas of an application or service we like to have. The Kubernetes stores the desired state in a data store. Then the controllers observe the current state of the cluster. And then if there are only two replicas are running, Kubernetes creates another one automatically to match the desired state. If a pod fails, Kubernetes notices the gap and creates the replacement automatically. If you update the desired image version from X to Y, Kubernetes starts moving the system towards that new version. So the flow is this. We always submit the R intent via YAML or an API request. The Kubernetes stores the desired state. The controller is actually always watching in real time. They take a corrective action always. It doesn't happen only once. It happens always. The continuous loop is what gives the Kubernetes a self-healing behavior. A good way to think about is Kubernetes is less like a script that executes just once. It's always more like a thermostat where you go and set the desired temperature, and the system keeps adjusting until the reality matches the target. Containers. Before we go actually deeper into containers, we need to anchor ourselves in containers first. A container packages an application process, its dependencies, and its file system, which can be a replaceable runtime unit. The container image is an immutable artifact we build and distribute to a registry. A running container is basically an instance of an image. Kubernetes doesn't usually build images for us. Instead, it assumes that the image already exists in registry somewhere, and Kubernetes pulls those images and manages, where and how it should be running. The distinction is actually very matter, right? So the Docker or any RSCI pipeline may create the image, which is stored in any registry. Kubernetes schedules and manages the running instances of that image. When something fails, Kubernetes replaces the running instance. It doesn't edit image itself. So the container image is the input, and Kubernetes provides the operating layer around it. The placement, the life cycle, the networking, scaling, health checks, configuration, and recovery, etc. Cluster model. A Kubernetes cluster has two major parts. One is the control plane. Another one is the data plane, which consists of multiple worker nodes. The control plane is responsible for decision making. It accepts the API request. It stores the cluster state into the etcd data store. And there is a scheduler, which is always running to schedule the work. And there are controllers, which are basically watching the state of the cluster, and it reconciles into a desired state. On the other side, the worker nodes, or where the actual application workloads run in terms of parts. Again, the separation is very important here. The control plane decides what should happen. The worker nodes makes them it happen by running to multiple parts and also reporting various statuses back to the control plane. Kubernetes becomes powerful because it coordinates many machines through one API and one desired state model. Let's look at control plane in detail. The Kube API server is the front door for the cluster, where all of our requests will go through the API server, like either through kubectl commands or any of the CI/CD tools, any other controllers for that matter, operators, or any other automation systems which wanted to interact with the cluster will go through the Kube API server. The API server does the validation of the request. It also applies the authentication and required authorization, and it exposes the basically a lot of watch streams so that controllers can react to changes. etcd, it is the consistent storage layer for the cluster state. It stores the desired state and also the current status for the Kubernetes object. The scheduler, which is responsible for assigning pending parts to the nodes. It looks for the resources, the constraints which you applied, affinity, tails, topology, and various factors before choosing which node is the best node to schedule a part. The controller manager, which is the reconciliation, which has the reconciliation strategy in which, where, for example, there's a deployment controller, replica set controller, there are job controllers, all work by watching the objects and it takes necessary action. In cloud environments, especially, there's a cloud controller which integrates the Kubernetes with the cloud provider. This how the Kubernetes can request the cloud load balancers and also work with the provider specific infrastructure behaviors. So the takeaway from this slide is the control plane is API centered and the components do not randomly mutate the cluster. They work basically through the Kubernetes objects and its statuses. Moving on to the worker node. So a worker node is where the workload actually runs. The kubelet is the node agent, which is running on every worker node. It watches for parts assigned to that node, and it asks the container runtime, which is also the part of the every worker node to start the container, also run health checks, and also reports the statuses back to the control plane. The container runtime is the software which is actually pulls the images and runs again. For example, a Docker container. Docker is the one of the container runtime. The networking is handled through components such as kubeproxy and the CNA plugin. The CNA plugin gives the parts IP addresses and also connects the pod networking to the cluster network. Kubeproxy or an equivalent data plane implementation helps implement the service routing. Each pod gets a shared runtime boundary. Containers inside the same pod share the same network namespace, which means they share the same IP address and can talk to each other through localhost. They can also share the volumes to maintain the state. The worker node always sends the status back to the control plane. It could be a pod status, or it could be the node health or the resource usage in the particular node, and also some of the conditions in the worker which should be healed. So it is based on these reports, the control plane makes the decision to self heal or to reset its parts. So essentially the pod is the smallest schedulable unit, a basic building block in Kubernetes. We do not actually manage the Kubernetes do not manage the containers individually. They manage and schedule pods. Most of the times, one pod represents one application or service or component, such as an instance of an API service or one worker process. A pod can contain more than one container, but that usually means the containers are tightly coupled and they need to share the networking or the storage for that matter. Inside a pod, the containers can share the same IP addresses. So if there are two containers, then they share the same networking and they can communicate to local host also. Also, they can define a shared volumes so that they can share their state. Um, the most important operational point is that pods are disposable. They can come and go. Can be deleted, can be rescheduled to some other node. We can be replaced for some reason. So the pods are not like a traditional permanent long-running service. So we should treat the pods as always a replaceable running unit as a temporary one. That is why the production workloads are normally managed in the control plane by the high-level controllers like deployments, stateful set, daemon sets, or jobs. These controllers create and replaces the parts in the Kubernetes architecture. Workloads. So the first thing, the important thing in the Kubernetes understand is the deployment resource. The deployments are one of the most common Kubernetes workload controller. Their deployment manages the replica sets and the replica set manages the paths. This ownership chain matters. Like we normally do not go and create the parts directly and then do not maintain them ourselves. Instead, a deployment resource will be created and you go and define what do you want. Like for example, how many replicas you want, which image this particular part should be using, and what are the update strategy, etc., including the health checks, etc. The deployment controller then works to basically the maintenance state. If you request for number of replicas, then that deployment resource ensures that that many number of parts are available at given point of time, at any point of time. If, for example, if there is one node, one part fails, then the replica set automatically creates a replacement. And if you go and update the image of the part, it ensures that it creates those new parts based on the rolling strategy you have defined. The deployment also gives us various ways to define your release behavior. For example, you can say that, hey, I want to replace these parts using rolling update or rollback history, etc. Right? So this ensures that you get the required availability in your cluster for the services you are running. Services. As we talked about, parts are the temporary unit, so we cannot rely on their IP addresses because those IP addresses can change as and when new IP address parts come up. So we need to have a very a stable networking identity for the parts, so which happens through service. A service is another resource in the Kubernetes which gives a stable network identity which actually fronts in front of the parts. So instead, the clients connects to parts, they reach to service, and service in turn directs the calls to respective parts. The service usually finds the matching parts using labels. So when you create parts, you define the labels in each part, and when you create a service, you can mention that this particular service can route can basically route the request to the parts which are grouped under this label. So the core pattern is the parts are always replaceable. and services provides the stable access to those groups. So it means that the application which are consuming these services can rely on service name instead of tracking the individual pod IP addresses. Edge traffic. A service gives the stable access inside the cluster, but there are many applications also need traffic from outside the cluster. So that's why the ingress and gateways are part of the clusters, are part of this ecosystem actually. So when a typical request starts from a client, reaches an external load balancer, then it flows through the various rules defined in the ingress and the gateway routing rules. These rules look at the various parts of your request, like either the host names or path. Then they can forward the traffic to the appropriate service based on the request coming in. Then the service in turn, we know that it actually turns the traffic into the matching parts. So this separation is also very, very useful where the application parts do not need to know about the public DNS and TLS termination or existing routing rules. The service provides a stable backend, and the ingress or gateway handles the external HTTP routing, which is happening from the actual client. In the latest Kubernetes environments, the gateway API is becoming more expressive and role-oriented way to manage the traffic routing. But the concept is simple. The external route rules point to internal services, and the service points to pods. Configuration. The configuration should not be actually baked into inside the application, so it makes the application specific to certain set of configurations. So the way it should be is that the single image which should be used for various environments of dev, stage, and prod, or even for different needs. However, the configuration which can be fed outside of the image will change the behavior of that service. So in case of Kubernetes, it is achieved through config map to secrets, config map for non-sensitive and secrets for sensitive values. For example, like passwords or tokens or API keys or even certificates to be maintained, secrets can be used. Both the config map and secrets can be injected into parts as environment variables or mounted as files. The mounted files are very, very useful for structured configurations, certificates, and there are application settings that sitting on the disk. One important thing to know is that the Kubernetes secrets are not automatically complete security solution, but apart from that secret, still you need to apply a role-based access control mechanism. Also, you should ensure encryption happens at rest, and all of the good operational practices in the market. So the principle is simple. You should keep the images immutable and provide the environment specific configuration runtime instead of baking into the image. Storage. State applications are usually expected to be stateless, but that's not the case always. There are cases where you have to start maintaining the stateful applications. So for example, the databases, queues and file stores and other stateful workloads need an explicit way of handling the storage. So there are many storage applications Kubernetes uses where a pod declares that it can need a volume and a persistent volume client or a PVC, which describes the storage request, for example, how much size, how much, what's the access mode, what are the storage class I wanted to do it with respect to PVC. And the storage class describes how the storage should be dynamically provisioned. Um, so the actual persistent volume or PV, which represents the actual backing volume. This abstraction is very, very important because it lets the application declares the storage intent without explicitly mentioning that where is the exact storage is, especially where is the cloud disk, where is the storage backend into the pod spec. The important point is that the pods can always be replaced. So it means the data must be survived outside of the pod. So we should definitely maintain the storage separately from the container file system because the containers can come and go at any point of time. So for the stateful workloads, we also need to think about the backup, also the restoring it and replicating it, the access mode for the performance, and also need to think about what happens if the load fails. Scheduling. Scheduling is the process of defining where pod should run. The scheduler considers many inputs. For example, it uses resources, selectors, pains, and topology as is in the slide. The resource requests tell Kubernetes how much CPU and memory the pod needs, and the node selectors and affinity rules can require prefer which node you want to schedule this part, and the taint and tolerations define that you can actually reserve the nodes for a specific workload, and the topology uh, basically gives the rules to distribute the parts across zones, even to reduce the failure risk. The common mistake think that is to assume that the scheduling is very, very random, but it is can be very well defined and managed by the user. So when we troubleshoot the scheduling, it is often the fastest to starting point. Shows that there are scheduling failures or placement failures because the constraint mentioned for the scheduling actually has not met. Moving on to health. Kubernetes definitely needs to know the way to understand the application health because it makes the decision based on these health metrics. There are various health measuring mechanisms. There is a startup probe, readiness probe, and liveness probe. The startup probe answers the simple question as the app reaches starting. And readiness probe answers to traffic is sent here. If it has failed, if it is not as succeeded, any of the requests coming to this pod, the service will not route the traffic to this pod until this particular state becomes active. Then the Linus probe is if the application basically it checks that the application is stuck or is unhealthy, so that it sends some reports back to the control plane to make decisions because the decisions are required to maintain the desired state. Scaling. So Kubernetes provides a very good mechanism to scale your services either horizontally or vertically. So there's the horizontal pod autoscaler exists, HPA, which allows the number of parts to be changed in runtime based on the metrics like the amount of CPU or memory or even any of the custom application metrics. If they reach any threshold, then the HPA can add or reduce the replicas. So based on that, the number of parts will increase or decrease. Then there is a vertical fault autoscaler, which focuses on the resource request. Um, it is it recommends or adjusts the CPU and memory request so that the workloads are sized more accurately. There is a cluster autoscaler, which works at the node level. Um, if there are if the number of parts scheduled on the node has reached a limit, then based on this definition, additional number of nodes can be added or decreased. Also, you can define quotas and limits for the part of scaling. It is they actually prevents the namespace or the team from actually consuming the unlimited resources, which is essential for maintaining your allocated cost and budget. Releases. So Kubernetes supports rolling updates, which is a very crucial for maintaining the high availability. This means that there is a gradual release of your version happens, so that you do not have any interruption in your service. So during the rolling update, what happens is that the Kubernetes creates a new part of the new version first, and it actually waits for them to be ready. Then it shifts the traffic, and then it scales down the whole version so that the interruption is minimal, so that customers' impact will be minimal. Moving on to multi-tenancy. So in the real clusters, there will be you can have more than one team share the cluster. For example, there is a concept of namespaces where your teams can define and maintain and manage their services inside a namespace. Also, you provide a security role-based access control mechanism, which defines who can do what on the cluster. So which includes basically the concept of role and role binding. You define the role where what type of actions are allowed on what resources. For example, a role can be saying that reading a pod or managing deployments, and the role binding is the resource which attaches that role to any user or a group or a service account for that matter. Observability. Um, so Kubernetes requires this observability to take decisions. So the metrics tells us all of these measurements like what is the CPU memory, the request rate, the error rate, health, etc. The logs, which they give us what happened, which is helping for debugging purpose, and events tells us what happens with the Kubernetes decisions, like if there are any failures in scheduling, or if there are errors during image pulling, or there are mount failure errors, even what happened with while scaling up or down. And there are traces which shows us how the request moves across services uh, when the request comes in. Security. So Kubernetes provides a layered security. There is no single switch. You need to ensure that you use this layered security effectively to secure your overall ecosystem. So it starts with supply chain, where you have a very trusted images. There is a vulnerability scanning for the images, only signed artifacts, and there's a controlled registries that are very crucial for ensuring that there is the supply chain is very secure. There's admission control. I'm sorry. There is identity and authorization, where it provides a role-based access control mechanism where you define roles and also which binds to a specific user or group or for the service account for that matter. Then there is admission control, which actually validates the objects before they are stored into etcd data store, which is very crucial to ensure that um, um, to ensure that the only the accurate objects are stored in etcd. Then there's another network security layer security exists. There's a network policy which can control which parts can talk to which parts. That kind of level of security is readily available in Kubernetes. And also there are control ingress you can place before the services, which ensures that your external exposure is very well managed and restricted. And there is also runtime security, where you can have a very settings on your pod level security, and you can have only read-only file systems to avoid writes, unwanted writes, and also running as non-root, which basically ensures that you don't accidentally do something wrong, and also do the limited privileges delivery. So the as Kubernetes usage is grows, then the way you go and apply those manifests becoming more cumbersome. So we need additional tools to help you to manage those manifests, like Helm and or Customize or GitHub. So Helm is one of the very important, famous the packaging system, which tool which gives the which gives the way of managing your Kubernetes resources charts. Um, the Customize lets you compose and patch the manifest for different environments without doing any templatization. GitHub is used your repository as the source of truth and continuously reconciles the cluster towards what is declared in the Git. So what is the common delivery flow is, yeah, developers, they only change and manage the manifest, and the change is actually reviewed and managed and approved in the pull request. Then automatically the policy check runs, then the final configuration is rendered. Then the GitHub controller, which is part of the control plane, ensures that those requested changes are applied to the cluster. So this gives the teams the auditability and accountability. So if there are any mistakes or bad decisions happen, it could be easily found and routed back. Um, so the goal is it should be a reviewable, it should be a reproducible cluster. Moving on to troubleshooting. The fastest Kubernetes troubleshooting path is following the ownership from top level intent into the pod's reality. So you can start with your deployment object, and you can describe your pod, and you can get your pod details and describe your pod itself. You can look for logs for what does the process say, and you can also look at the events of the in the cluster, what type of event occurred with respect to these parts, which are which helps the troubleshooting to easily find out the error. Okay, what's the takeaway from this session? So the final takeaway is that the Kubernetes workload should be declarative. It should be very easily observable and also replaceable. So we have to use the top level resources like deployments, stateful set, daemon set, jobs, etc., instead of parts. So these top level resources sets the request and limits intentionally, and we also define what is your probes, like what is the startup and liveness probes and readiness probes based on your application behavior, and keep the configuration and secrets baked out of the images. Um, and Services should be used for stable communication, and ingress controller should be used for maintaining your external traffic coming from the clients. And the automatic delivery happens through reviewable workflows through GitHub or through other tools like Helm or Customize. Then you do a least privilege mechanism. You achieve those things through using namespaces or role-based access control or using service accounts. When you debug, you can debug using the who's the owner and also the recent events. So Kubernetes always constantly tells what it's trying to do. So it's up to the developer or engineer to go and look at the available debugging tools to ensure to find out where is the error. So Kubernetes is at a high level is a reconciliation system. You declare the desired state. The Kubernetes keeps working in the background to make sure the real system matches. It is. Um, Everything else like the parts, the services, the deployments, the probes, auto scaling, security, and delivery, they all fits into the mental model. Thank you, everyone. That's all I have.